Now, we have different types of sequences that exist. Anytime we get from one term to the next by adding a constant, so adding the same number every single time, whether it's positive or negative, we call that an arithmetic sequence. Anytime that we get from one term to the next by multiplying by the same number, we call that geometric. And then there are other sequences which are neither arithmetic or geometric. So a sequence just means that going from term to term to term, there's a pattern, but it doesn't have to be always adding the same thing or multiplying by the same thing. So we could say that we have the sequence of the prime numbers. We can figure out what the next number is going to be because it's going to just be the next prime number. We could have the Fibonacci sequence, where it's created by adding the two previous numbers together. So we have 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And then logically, next would be 8 plus 13 is 21. So on and so forth. So sequences we consider as either arithmetic, geometric, or just other. Other just fits into a pattern, but it's not a constant multiplication or addition that's taking place. So, all of the examples that we had on the previous page were either arithmetic, or geometric. The arithmetic ones were all the ones where we added by a set amount, whether it's positive or negative, and that was tables A, B, E, and F. The geometric ones were where we multiplied by a set amount, whether it was a whole number or a fraction, and that was tables C and D. We can also have what's called a finite sequence, which means that it has an endpoint, and that's always listed where either all the listed or numbers are listed, or it will show you a certain set of the numbers to show the pattern. It will include an ellipses to say that there's more numbers that existed in between but kept the pattern going, and then it will state a final number at the end, which means that those are all the numbers that exist within that sequence. We can have what's called an infinite sequence, and an infinite sequence will always end in an ellipses to indicate that that pattern is going to keep going on forever. And there isn't actually an endpoint. It's just going to keep happening, up into the billions and past. If we show the sequence as a function on a table relating the terms to their term position or term number, the domain is always going to be in the function of natural numbers, and the range is going to be the set of terms of the sequence. So my domain is always going to be 1, 2, 3, 4, 5, however many terms there are that exist, and it could keep going. My range is just going to fit into whatever those actual numbers would be. And we can see that when we take the information from table A, 1 was 3, 2 was 6, 3 was 9, 4 was 12, and 5 was 15. When we go to table B, 1 was 1, 2 was 3, 3 was 5, 4 was 7, and 5 was 9. For table C, we had the value of 1 and 1, 2 and 2, 3 and 4, 4 and 8, 5 and 16, 6 and 32, 7 and 64. For table D, we had 1 and 32, 2 and 16, 3 and 8, 4 and 4, 5 and 2. Table E was 1 and 1, 2 and 5, 3 and 9, 4 and 13, 5 and 17. And table F was 1 and 8, 2 and 4, 3 and 0, 4 and -4, and 5 and -8. And we can see that all of ours that were arithmetic created linear functions. All of the ones that were geometric created nonlinear functions. So, a sequence in which the next term is determined by adding a constant is arithmetic. This sequence can be represented by a linear function. Anytime that I have a sequence which is determined by multiplying a previous one, it's going to be geometric, and geometrics are always non-linear. All right, go ahead and try some practice with this.